Hello everyone and welcome back. So I'm going to start where I left in the earlier video. So I was discussing some definitions, and I discussed about the definition of positive semi-definite operator. But let me tell you how the Google definition, or the definition that I know, and the definition that is given in that book are equivalent. Uh, I thought about it after ending the video, but I can tell you what I thought. So I told you that an operator is positive semi-definite if all of its eigenvalues are non-negative, right? That means if the eigenvalues are a and if it's greater or equal 0, then these are called PSD operator. So how this definition is equivalent to that definition, that a positive operator A is defined to be an operator such that for any vector V and A acting on V, the inner product between these is real and non-negative. That means this is non-negative. So a connection can be made like this: if V is an eigenvector of this operator A, and then if A is the eigenvalue, then what is the then we get equivalent expression for this, right? So if we plug this expression here, then what do you get? V A V, right, the inner product, and then we get A V V, right? And we all know that this norm is always this norm is greater or equal 0, right? So if the eigenvalue is greater or equal 0, then actually it gives you the same definition that I have given here. So that's how these two definitions are equivalent. Anyways, so the topic of this video is about spectral decomposition, writing a normal operator in terms of spectral decomposition, and then we'll define a function for that operator, and blah blah blah. Well, uh, sorry, just I was just being too casual. Anyways, so let's say we have an operator A, and this operator is normal. That means A dagger A is equal to A dagger. So this is a normal operator, and if this is the normal operator, then it can be, there will be a spectral decomposition for that normal operator, and this spectral decomposition, let's say, is written in terms of this A basis. So this is the spectral decomposition, and now consider that we have a function. So if we have a function and it's taking the complex number A, and it gives us the is taking an input function, a complex number A, and giving also a complex number B. That means it can be viewed like this. If this is the function, it's taking input a complex number and giving us a complex number B. So this is the function. If we have this function, then we can define a function for the operator A. This A is put here. So we are gonna define the function like this. Again, sum over A, and now we are as coefficients, we are writing the function f of A, and writing in terms of this basis A. So how we can expand this function? We can expand this function like this: A1 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 Kate A1 bra plus A2, 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 I mean bra and cat, and we are writing in outer product form. So dot dot plus an cat bra, like this. So this is the expansion of this operator in terms of the basis ai. So I is equal to 1, 2, 3, and n. Now the corresponding sum for the function that we have defined for this operator are f1. So earlier we have written the coefficient a1, and then we are taking the coefficient as an input for the function, and the output is written as coefficient for this definition. So a1, a2 plus function of a2. I made a mistake here. There should be a 1. Okay. So like this, and f a3. Oh, sorry, fn an an. So the corresponding summation will be like this. So then the next statement from the text, look, I'm just copying the text. So nothing from my side, just reproducing what is written in the text, and I'm just trying to explain from my experience. So what is the next sentence that is written here? A little thought shows that this uh, function of this operator a is uniquely defined. And what is that little thought? I can tell you what is my little thought. So I have thought. So the point here is that we have a spectral decomposition of this operator a, right, in terms of the basis ai. So in terms of this orthonormal basis, I guess it's orthonormal, and if it's orthonormal, so in terms of this orthonormal basis, there will be a unique way of writing this operator. So if this spectral decomposition with respect to this orthonormal basis is unique, then if we define the operator, the function of this operator like this, and taking as input of the corresponding AIs, and in terms of this AI basis, then again this expansion will also be unique, because we are writing in the same basis, right, in the outer product form, right, and this is are just the corresponding outer product form of these basis elements. So that's why in that sense it should be unique. So I'm going to stop here, because I wanted to make this video short so that you can watch at your convenient time. And as I said, there might be some confusions and you are not understanding what I'm trying to say. And so after making several videos, the plan is then we can fix a date, and then we can sit together to discuss about what we have discussed during these videos. So right now it's from the discussion from my side, but whenever we will be meeting, then we can make a fruitful discussion contribution by taking contribution from both sides. So see you in the next video.